Okay, now we are going to look at the topic of pulse width modulation. So in order to understand pulse width modulation, the first thing to understand is what is digital to analog conversion, right? We have already looked at analog to digital conversion. We know that there are sensors that can pick up real world signals and convert them into voltages, and analog to digital would basically take that voltage and convert it into a number. There are some cases where I want to do the opposite, which is to say that I have a number and I want a voltage that is representative of that number, right? Now, there are many applications, as we will see, for something like this. An example of this would be, let's say that I want to generate a voltage in the range of 0 to 3.3 volts, right? And maybe my numeric input is 10 bits, just like the ADC was 10 bits. Maybe my DAC, digital to analog conversion, is also 10 bits. So I give it a number between 0 to 1023. Now what happens is that, let's say I wanted to generate a value of corresponding to the number 400. What would happen is I would take this 400, multiply it by 3.3 volts, divide by 1024, which is the step size. 3.3 volts divided by 1024 is your step size, which means that the number 400 should ideally correspond to the number 1.289 volts. Now clearly this is already over specified, because I know that my resolution is only 3 millivolts, so I can't really get 1.289. I can only say 1.289 plus or minus 3 millivolts basically, right? And not just that, this is an ideal value. In reality, there will be the quantization noise, which means that there is the actual resolution step size that you have. There will be random noise, which could be temperature related, it could be related to how your circuit was built, and there could be non-idealities, which means that the number 400, even though ideally I would want it at 1.289 volts or so, might end up getting mapped to something higher or lower in a systematic fashion. Every time I give the number 400, it might give me a wrong value, off by a certain amount, right? That's more like a systematic deviation rather than a noise which is expected to be random. But the bottom line is, there can be scenarios where I would actually like to see this kind of behavior. I give it a number, I want to see a voltage that's related to that number. So what we do instead, the alternative approach, so the bottom line is, yes, just like we built analog to digital converters, it is possible to create digital to analog converters as well, right? And they would take in a number and they would generate a voltage that is proportional to that number. The point is, in a lot of cases, it turns out that's a bit more complicated than we really want. The circuit for doing the digital to analog conversion is not a very trivial circuit. It does require a certain amount of work. It's not the most complex circuit in the world, but we would like to simplify if we can. And here's a way of simplifying it, right? Basically what we say is, let me look at some kind of a high speed clock where I have some kind of clock period and a frequency so that t is equal to 1 over f is the clock period. And what I do is, I basically generate a signal which is, all I do is, the signal is either 0 or 1. It's this blue curve that I have out here, right? So I say that I am either going to be at 0 or I am going to be at 1, and the way that I am going to do it is, I will switch over from 0 to 1 for maybe 2 clock cycles, then I will switch back to 0 for 3 clock cycles, go to 1 for 2 clock cycles, go back to 0 for 3 clock cycles, and so on. And what effectively happens as a result is that at the output, right, somebody who is seeing the signal from the outside, especially if you sort of see this, if this switching is happening fast enough, I'm not really going to see each of these variations. What I'll end up seeing is some kind of an average value. And what is that average value going to be determined by? How long was the signal on versus how long was it off, right? So I have some overall period of the signal which is given by this t on plus t off. Out of that, I have some time for which it is actually on, and this ratio t on divided by t on plus t off is called the duty cycle. Okay. Now that duty cycle multiplied by the actual voltage corresponding to the on value, right, is going to give me my long-term average value at the output. In this case, if it's on for 2 cycles, off for 3 cycles, I can expect that 2 by 5 or 40% is my duty cycle, right? And as a result, if I had 3.3 volts as my plus supply, I would get 40% of 3.3 volts, which is around 1.29 or so, right, or 1.3 volts as my actual output, right. So this approach is what's called pulse width modulation. Basically what it's saying is that you can think of this part over here as a pulse, which is a part of an overall time period, and by changing the width of this pulse, that is for how long it is high, right, I can get pretty much any average value between 0 by just keeping it off all the time to VDD by keeping it on all the time, right. Any value in between can be obtained by changing the duty cycle of this pulse, right. So pulse width modulation basically depends on or relies on a high frequency clock and some kind of a timer that basically counts up to T on and then up to T off, and during that time while it is in T on, some signal is kept on, after that the signal is turned off, and by controlling that I can basically get any duty cycle that I want. Okay. The resolution, how finely can I sort of vary the output that I see, is going to be determined by T, but you also need to understand that the actual voltage that I am going to see over there is not exactly that duty cycle into VDD. It is only that value on average over a long term average. So how do I get this averaging? It turns out that averaging is the equivalent of what's called low pass filtering, right, which is sort of an implicit physical property of most physical systems, right. If I have something that's varying very fast, when I look at it from outside, pretty much all that I see is the average value, right, because I'm not sensitive. My either if I'm looking at something, then my eye is not sensitive enough to the high speed variations, or if I'm sort of sensing, or if I'm trying to touch something, or if I'm trying to measure something, the measuring system is only sort of sensitive to the average value rather than to those high speed variations, which it sort of just rejects as more or less noise. Okay. So this average signal value is what we want, what we get at the output, and the interesting thing is, without having any analog circuitry, actually I have managed to get a very low complexity digital to analog conversion. I have managed to create an output signal that basically looks like an analog signal, right, without having to go through an actual analog process, right. Now in terms of what the code for something this would look like, right, this is the C code, it's not the Arduino level code. You would actually need to do something like this. You would basically use certain concepts that are there as part of the C, the programming APIs that are, or the software development kit, the SDK APIs that are given to you, right. You can basically define something called a timer, which is a structure in C. This is part of the HAL, the hardware abstraction layer, right, which basically says you can just set things like, you use a prescaler of a factor of 16, assuming that you have a 16 megahertz clock to start with. Okay. So you have a 16 megahertz clock, you give it a prescaler of 16, it divides by 16 and you get a 1 megahertz clock, right. And by doing that, I then say that the timer period is 1000. I also give it a timer comparison value of 500. And basically, effectively, implicitly what this is saying is that because I have set the mode over here to PWM mode, there's going to be a counter that's going to count high for 500 cycles and then remain low for the next 500 cycles, right. And what is the clock that it gets? It's 16 megahertz down converted by a factor of 16, so 1 megahertz. Therefore, this timer that I finally get is going to be something that looks like 500, so yeah, for 500 microseconds it will be high, for 500 microseconds it will be low, and what I will finally end up with is a 1 millisecond or a 1 kilohertz signal, right. Now at 1 kilohertz I am essentially sending out this square wave like this, right, which means that from the outside world, if something is not really responding to something as fast as 1 kilohertz, what it will see is an average value, right, which just looks like 0.5 of whatever 3.3 volts or VDD, right. and by changing this compare values to, let's say, 300, I could easily get 30% duty cycle, right. So these kind of changes can be easily made in by just sort of changing the comparison value, the period, and so on. You can get pulse width modulation of different sort of behaviors. Now you might wonder, why did we use this prescaler, bring it down, and so on? Because sometimes by having extremely high PWM frequencies, that can cause other kinds of issues in terms of interfering, generating signals that are interfering with other kinds of electronics around you. So you don't always want, even though you have a 16 megahertz signal, you don't want to run it directly, your pulse width modulation directly at 16 megahertz. It makes more sense to bring it down to a safer frequency that can be used, right, which will generate less interference with the rest of your system, as long as that frequency is still high enough so that your physical system that is being driven does not really rely on, or does not depend on what you are doing over here. Okay. There are many applications of this, by the way. A common one is that you can actually use this for LED brightness. So the dimmer controls in LEDs, right, you are probably aware of how LEDs work. They have a sort of cut-in voltage, a forward voltage, beyond which they are for all practical purposes on, right, and below which they are off. So LEDs, unlike the incandescent light bulbs, right, the ones with like the tungsten filaments and so on, just by increasing the current through it, you can't, the variation in brightness is a second order effect. It is not directly proportional to the amount of current, and in fact increasing the voltage and hence increasing the current through the LED is usually a bad idea, right, because they tend to have that very sharp variation with voltage, means that you can easily actually damage the LED if you end up sending too much current through it without really getting the kind of benefits in brightness that you would like to see. So if you want to control the brightness of an LED, what do you do instead? One way of doing it is pulse width modulation, right, and essentially what pulse width modulation does is that it sort of turns the LED on, off, on, off, on, off fast enough that for all practical purposes, as far as the LED is concerned, it is being turned on and off at such a high frequency that a person looking at it sees only the average amplitude or average intensity of brightness coming out of the LED. The LED itself is not glowing at half brightness or 1/3 brightness. It is either on or it is off. But because your eye implicitly cannot see things that are varying at 1 kilohertz, it automatically does an averaging and tells you that, hey, this looks like an LED at 1/3 brightness. Okay. Similar things can be used for motor speed. What happens with motors is that, once again, there are scenarios where rather than trying to explicitly say that by sort of controlling the speed at which the motor is being turned, or in order to control the speed at which a motor is being turned, you might want to change the voltage that's being applied to it. The alternative is to use PWM. You basically turn the motor on, off, fast enough that on average it ends up going at a certain speed, and by essentially increasing the duty cycle, it will turn faster and faster. By reducing the duty cycle, it will turn less and less, and therefore it effectively gives you the illusion that it's just going slower, whereas it's actually turning on and then off for longer durations. That's the actual thing that's happening. In both of these cases, the properties of the physical system are what is actually giving you the implicit averaging process, right? Either the eye is not able to respond fast enough to the LEDs blinking, or the motor's inertia keeps it going so that it averages out and gives you a certain speed. There are many other applications. Power delivery, you are probably at least have heard the term SMPS, or switched mode power supply, which is used in most electronic systems including laptops and so on. There are communication systems where they can be used sometimes for certain kinds of waveform generation, though not very common there. Temperature control and things like that, where you can either just turn on or off. Maybe it's an air conditioner and you don't really have a very fine grained control over the output temperature of the air. What you could do is just turn it on, then off, on, off, such that it averages out to the right speed. In general, what you are doing is a generic form of digital to analog conversion, right? The simplicity is the primary benefit. you don't need separate circuitry to do digital to analog conversion. It is also quite efficient because your circuitry itself is always operating either in the on state or the off state. It does not need to operate in some kind of intermediate state. In particular, certain kinds of leakage currents and so on can be avoided, right, by doing this. And you can get fairly good precision by choosing a high enough clock. Having said that, there are obviously some drawbacks as well. One of them is the fact that although your clock does give you precision control, it also limits your resolution and response time. Right? Some of the bigger problems with PWM are the fact that this high speed switching in turn can actually cause radiative effects. Right? You can actually have things where you are effectively generating radio waves at some other frequency which can escape from your PCB and then just radiate out into the air and interfere with other devices around you. Right? They can even sometimes create an audible buzz, right? That can be, I mean, if you go down into the kilohertz range, and you might have experienced this sometimes with UPSs and certain kinds of switched mode power supplies, that there is some kind of a buzz that you hear while they are operational, which is partly because of the rate at which this switching is happening. Right? And not only that, if you have a system where there is your digital circuit and you also have some sensitive analog measurements that need to be performed, this kind of high speed switching can end up causing leakage of that signal, right, through some inductive coupling and so on onto different parts of the circuit, and thereby interfering with your analog measurements. Okay, so this requires fairly careful design at the circuit board level, and bottom line is, it's for simple applications, of course it's the easiest way to go, but depending on the kind of application you have, you might actually need to design your board, your system, your environment, everything carefully. So this is an example in order to show how the same idea of pulse width modulation can be used in order to control, let's say, LED brightness or the position of what's called a servo motor, which I'll talk about briefly. Now, unfortunately, this example does not work directly with the STM32 simulation, right? Although we will try to sort of set things up so that you can actually use an STM32 board at some point. So what I'm using over here is the Arduino Uno as the simulator. Now, why does it not work with the STM32? It's a software limitation. The simulator does not support the timers that are required for doing pulse width modulation demonstrations over here. Right? Okay, so how does it work? Basically what we say is the potentiometer pin is A0, just like in the case of the analog circuit. I've basically taken a potentiometer and connected it up over here so that this signal, right, is PWM is able to generate an analog value, and as I turn this thing, the value that's being read back from the potentiometer would be something between 0 to 1023. Okay, so far so good. I also have an LED pin which is just pin number 9, and what I do is I set the LED pin as output. The potentiometer pin by default is an input. I need to actually initialize it as an analog mode, but that's the default state anyway, so it doesn't matter, right? I also initialize the serial port just so that I can print the values out on the screen. And what I do in the loop is I basically read the value from analog, I convert the value which I get over here, which is a sort of convenience function provided in the Arduino libraries, which basically tells you that you take the value from 0 to 1023 and map it into the value 0 to 255. Now why 0 to 255? Because it turns out that the analog write function, which is Arduino's equivalent of how to do PWM, assumes a value between 0 to 255. So what does this mean? Like, if you think about it, right, all the details that we said, that there's a timer, there's a duty cycle, there is some prescaler, all of that stuff is just being hidden away. It's abstracted for you, and all you get is a function called analog write, which allows you to give it a value PWM, right, and implicitly it sort of creates a pulse width modulated output for you. The flip side, right, not only do you not get control over the prescaler and the various timers being used, it also limits you to 255 levels or 256 levels, right? So these are trade-offs. What the Arduino ecosystem has done is it has said that for most practical purposes, at least for a lot of useful applications, having this simplicity allows you to get started and going with it much more easily than worrying about every single setting inside the HAL of the system. Not only that, this code could pretty much be migrated into the STM32 series with very minimal changes. All that somebody needs to do is figure out how to write an analog write function over there, which will automatically set up the timers for doing pulse width modulation, assuming that they take a value in the range 0 to 255. Yeah. How does it work? What happens when I run this is that you can actually see that this LED seems to have turned on. Where it gets interesting is if I slowly sort of try changing that value, you can sort of make out that the brightness on the LED is changing, but it's not very easy to sort of make out at this level, right? Another similar application of this pulse width modulation is in something called servo motor control. Now, servo motors are a very specific type of motor. They are meant for position control and not for speed control, right? And what happens in the case of a servo motor is that it takes in two signals, which is the actual voltage and ground, but it also takes another signal called the PWM signal, which is basically supposed to be an analog signal. And what happens is, depending on the value being provided to it as part of the PWM, the angle or the position at which this is oriented can be changed, right? So in this particular case, when I run this, I can see that, for example, as I move this thing, I can basically turn the position to which the servo motor is tilted, right? It has a sort of limited range of operation. When I go outside that range, it sort of flips out and ends up with the wrong value. And similarly, when I go outside the range in the other direction as well, it sort of just saturates somewhere, right? But within the range that I have, I can actually sort of get it to move around just by turning the potentiometer, which implicitly is changing the analog value being read in. That in turn is giving a different PWM value to the servo and changing the orientation at which it points. So once again, the bottom line over here is that this code is easy to use, but has hidden away a lot of the power that you get in terms of controlling the different capabilities of the PWM as well.